Welcome back to the EXD. The goal of today's episode is actually to give you a feel for how your input vectors are rotated, squeezed, stretched, and squashed inside a transformer. This intuition and tactile sense of mathematical operations is essential to the way I learn. I kind of need to feel my way around these things to make them stick. So today we'll take a small break from the usual EXD way of working with actual models and do some linear algebra, some theory, but in a very practical, kinesthetic sort of way. My name is Ram, and this is an open learning log that I call the EXD. To start at the beginning, check out episode 1. I'll link it in the description below. Okay, let's start. We have been walking through the first input step of the Quen 3.6 35 billion A3B model, and we already know that your input text is converted into tokens, which are then converted into vectors in a 2048 dimensional space. And we already started doing some linear algebra on it. We saw that in the MROPE episode, which is the last episode, right? Where you take your sort of statically looked up input vectors and rotate them a little bit just to kind of encode the relative position of that particular token in the entire input string, right? Then this vector, which has already been, rotated a little bit, goes on to get normalized. It actually gets projected up into a much higher dimensional space than even 2048. It actually kind of gets projected up into, two 4096 dimensional spaces. Some dot products happen between them. We'll refresh ourselves on what a dot product is between vectors to create what are called attention scores. The famous attention is all you need paper. Then it's normalized again. Then it goes... they're routed into a network, into the feed-forward network, and these vectors are then stretched, squeezed, squashed in this high-dimensional space, then finally normalized again, projected down back into the 2048 space, so that based on the logics, we can select the next token to output. Okay, so the journey of a vector through a large language model is one of being kind of squeezed, stretched, and rotated, projected up, projected down in multiple different places. And before we can really get a strong understanding of each step, it's good to have a feel for this. It's good to feel like, oh yeah, if I take a rotational matrix and multiply it with a vector, then I get a new vector which is slightly rotated but has the same length. If I project it up, it goes into this higher dimensional space. I can project it back down by doing this multiplication. It's good to have that feel. And that's what this episode is all about. Okay, it's going to be a quick one. All right, so this is not the article we want to look at. We want to look at linear algebra for transformers. Okay, so this is on Hugging Face. I'll link it below in the description. And the goal is to develop a feel for what happens inside a transformer. Okay, this is not going to be the actual transformer, this episode. And as always, I have a companion Jupyter notebook, which you can open. And actually, this one you can actually open in Colab. So let's quickly do that. And let's just set up our space. I'll move this to one side and I'll keep the article here. I really suggest you do this. Keep them side by side and kind of go through each step so that you can not only read what's happening, but you can see the code that executes it and produces the images that you see in the article. You can even change the code and play around with it to see what happens. Okay? All right. So linear algebra for transformers. Now, one of the things we're going to do, and if you remember, I mentioned before that Geoffrey Hinton said, don't worry about 2048 dimensional spaces. Okay? When you're thinking about high dimensional spaces, we know how things work in 2 and 3 dimensions, the dimensions that we can kind of perceive. So just do that, do your operations in that, and then just realize that it just simply generalizes the same way to higher dimensional spaces. So what that means is if I rotate a vector here in two-dimensional space, okay, I'm rotating it in 2048 dimensional spaces, but rotation is rotation. Okay, so the entire episode today is going to happen in 2 and 3 dimensions. And this is just to get a feel for what's happening. So that means instead of encoding cat and dog in 2048 dimensions, we just encode it in these 2 dimensions. Okay, so let's assume for now that cat is this vector, this blue vector, 0.8 and 0.3, right? 0.8, 0.3. And dog is 0.6 and 0.7. So this is 2 vectors kind of pointing in the same direction. They both are furry animals, so some intuition there. But yeah, vectors represent tokens. Cool. So let me just run this. So vectors are just these numbers, and you can produce, their visualization. Now, the first thing that we did to this input embedding, the second you convert your text into a vector, is we rotated it, right, in mrope to embed some extra information into it, And the way you do a rotation is you multiply it with the rotation matrix. So this is a counterclockwise rotation matrix. Basically, rotation by theta is a matrix in 2 dimensions, is a matrix of cosine theta minus sine theta, and cosine theta. Okay, and here you can see if you multiply these 2 vectors together, then what you get out is a new vector. Let me do it over here, which is slightly rotated. Cool. So here is cat. Okay, we already established cat over here, right? We said, listen, cat is equal to 0.8 and 0.3. That's a vector. Okay, we created the rotation matrix here. It's a numpy array, and here you can see the numpy cosine, numpy sine, negative numpy sine, and numpy cos, right? And we said theta is equal to pi over 6. That's 30 degrees. Pi is 180 degrees. 2 pi is 360 degrees. So pi over 6 is 180 divided by 6 is 30 degrees. Okay? So this rotates cat by 30 degrees. Right? And here's the answer. Okay? So this is our original cat. That's 0.03, and our new cat pops out here, right? This is our new cat, rotated cat, our cat. Okay, and we're just showing that the length is the same. All right, the norm of cat, which is the length of the vector, and the norm of rotated cat are both 0.8544. Cool. And of course you can just rotate them through 12 positions and eventually return back to the same place. Okay, so that's rotation. So we can rotate vectors by multiplying them with rotation matrices. We'll come back to this a little later. Okay, the next question we want to ask, and this is very important for our next episode on attention. How similar are 2 vectors? How similar are cat and dog? Right? This is an interesting question to ask, and it turns out we have a method in linear algebra. It's the dot product. The dot product between 2 vectors a and b produces a scalar, a number. Okay, it's not a vector anymore. And that number is at its highest value when a vector is multiplied by itself, and is at its lowest value when it's kind of multiplied with a vector which is exactly the same as it, pointing in the opposite direction. Okay, and the way you do a dot product is if you have a vector a and a vector b, then you multiply a1 with b1 plus a2 times b2 plus a3 times b3 and so on until an times bn. So it's just sigma ai times bi, where I is the index of the dimension. And it turns out that this is also equal to the norm of A times the norm of B times cosine theta, which is where theta is the angle between these 2 vectors. And that's left as an exercise to the viewer. You can figure out, this is high school algebra, trigonometry, or I guess linear algebra. So you can you can easily find resources to understand why this is the case. Okay, so let's just do some of this and get a sense of what it looks like, right? Let's see what these things look like. So here's cat times dog. If you remember, cat was 0.8 and 0.6, and we multiplied it with dog, which is 0.3 and 0.7, and so somewhat highish positive number, 0.69. But if you did cat with cat, you get 0.73, right? It's cat squared. Very similar to each other. Similarly, dog times dog gives 0.85. And cat with negative cat, where literally it's minus 0.8 and minus 0.6, you get minus 0.73. So high numbers if they're pointing in the same direction, and low numbers if they're pointing away from each other. So if you see this in a heat map, obviously the diagonal is every, this is like sort of the dot product of these things with themselves. This is actually exactly what the attention mechanism looks like. Imagine this is an input string and you just dot product it with itself, okay? And the numbers of either of the triangles are what you use. So cat with cat, as you can see, dog with dog, and negative cat with negative cat are all high numbers. And things like cat with negative cat are extremely small numbers, right? And with a random number, you just get something in the middle. So for example, cat with random is 0.11, neither here nor there. But at this point, you may have noticed a problem. Cat dot cat is 0.73. But dog dot dog is 0.85, which is a bigger number. But there really is no meaningful sense in which dog is more similar to dog than cat is similar to cat. We want these two numbers to kind of be the same, right? I mean, cat is as similar to cat as a dog is as similar to a dog. So this brings us from dot products to normalization. The reason this is happening is simply because dog is a longer vector, okay? It's distorting this relationship. So our solution is to do something called normalization. Normalization basically takes any distribution of numbers and sort of squeezes them all into a tight range where they behave normally, okay? So if we do this, and here you do it using the linear algebra normalization function, right? This is just a standard normalization function. If we apply it to our cat and dog vectors, then what we get, right, is this clean heat map. Now cat dot product with normalized cat, dot product with normalized cat gives you 1, just like normalized dog does with normalized dog. But it's not as if, and those vectors are slightly different now from the initial vectors. They've been normalized. Then they've been normalized such that this is always true, okay? So if you look at the Jupyter notebook, before normalization you had all this variation, and after normalization, cat dot cat and dog dot dog are always giving you 1, okay? This is just happening all over the place inside transformer, okay, in multiple places. In fact, every time we do some stuff, there usually is a normalization step that just, like you mess around with the input vectors all over the place, then you normalize. Then you do some more, then you normalize. This keeps repeating. Okay, so what we've seen so far is we've seen how to represent vectors in spaces, we've seen how to rotate them, we've seen how to get scores for how similar they are to each other. We've seen how to take a bunch of them and normalize them. Now, and in fact we already saw this, but let's see what else we can do with vectors. What happens if you multiply them with matrices, right? So matrix multiplication basically requires that the number of columns of the first is equal to the number of rows of the second, okay? That's the rule. And if you multiply a 2 by 3 matrix with a 3 by 1 matrix, what pops out, and let me just make this a teeny bit smaller so that you can see everything. is you get a 2 by 1 matrix, right? Let's do that again. 3 by 2 into 3 gives us back 2. So this is a three-dimensional vector, a vector in three-dimensional space. And by multiplying it with this 2 by 3 matrix, we squash this three-dimensional vector down into 2 dimensions. In some ways, you can think of this as a shadow of this vector on a floor, right? On a two-dimensional space. If you remember from the last episode, we're talking about the vector and its shadow. This is like a projection down. And this doesn't have to be the case. In fact, if you look at rotation, it's just the same thing, except we're here the input vectors in 2 dimensions and the output vectors in 2 dimensions, right? So look, this is a 2 by 2 matrix times a 2-dimensional vector, out pops another 2-dimensional vector, except it's rotated. Okay? So the rule is when an m by n matrix is multiplied with an n comma something matrix, the result is m. Okay, so if you do m by n and multiply it with an n-dimensional vector, the result is an m-dimensional vector. This happens all over the place inside an LLM and in Qwen 3.6. Okay, in fact, your input token, which we know lives in a 2048 dimensional space, is actually projected up into a massive 8192 dimensional space. Actually, it's 2 spaces, a query space and a gate space, each 4096. That's 2 of these dimensions. So here, see, look at this shape, right? This is a learned shape that comes out of training. This is the matrix that comes out of training. It's 8000, m is 8192, n is 2048, n is 2048, and out pops a vector of 8192. So this input vector has been projected up into this higher dimensional space. And it happens all over to produce like KV cache heads, the K heads, you take 512 times 248 to pop out 512. We'll understand all this later, we'll come to it. But this is just to tell you this happens all over the place. Okay, so this is projecting up and down. When we finally want to output a token, we're working in these higher dimensional spaces. We want to project it back down to our familiar 2048 space, dimensional space, so that we can produce an output token which lives in this space, right? Let's see it in action. Very simple. Here's cat, 0.8, 0.3. Here is some sort of up projector. It does something. It projects it up and moves it around in some unknown way. Okay. What you get is the 2-dimensional vector cat gets converted into a 3-dimensional up cat. And you can kind of think of this as, this here's cat, see? 0.8, 0.3, familiar old cat in a 2-dimensional space. This is now, pimped out cat in 3-dimensional spaces through some projection. And this is actually what the LLM is working with. It's working with this projected up thing. After doing all its work, it'll project it back down to give us an answer. Okay, so it's kind of lifting this vector. Imagine this vector is a stick on the floor, confined to the floor. You can like roll it around, you can point in a 2-dimensional space. Now imagine picking it up and holding it at an angle to the floor. Voila, you've got 3-dimensional vector. Okay? Cool. Now, obviously, if you can project something up, you can project it back down. So how do you do that? We know the rule. If I have a 3-dimensional vector, then I just need a 2 by 3-dimensional projection matrix to project it down to a 2-dimensional space. Okay, so here's the round trip. Blue 2-dimensional cat vector gets projected up. Imagine the LLM does a whole bunch of things to this, squeezes it, stretches it, does it. Then finally, when it's ready to give an answer, it pops it back down and you get the red vector. Okay. Please check out the code. Just look at it, look at what we're doing. Here's the array. This is the projection matrix. Here is our, the way you do the multiplication, use the @ symbol. write out all the values. Look at the input, it's 3 dimensions. Look at the output, down to 2 dimensions, right? Look at the original thing, so you've seen that there's a little bit of a shift, so on and so forth. This just is really good for giving you a feel for this. Okay, so this is actually it, guys. This actually covers basically what happens in a transformer. You have some text, you send it to an LLM. The first thing that's done is it's split into tokens. Those tokens each have a vector associated with them. So we have our initial vectors. Then we rotate them a little bit. We saw how rotation happens, right? To embed the relative positions of the tokens. Then we take dot products and create these attention scores, which we store somewhere for use later on, to show which tokens are similar to each other and which are very different from each other, kind of further embedding sort of this conceptual relativity. This is positional relativity, which we dealt with first. Here now we're dealing with positional relativity, like cat and dog are kind of similar-ish, but cat and fish maybe are not so similar, and cat and, I don't know, being late to work or lateness are very different from each other. So we're doing that. Then every time we do a step, we're like, oh, okay, we've manipulated the vectors. Let's kind of normalize them again before we go into the next step. So we often interpose a normalization step between two things. Then we say, okay, we want to work in a high dimensional space to do all this work. So let's project it up. So this happens. We expand the hidden state. And once the LLM does all its work, it actually projects it back down, as it has to a 2048 dimensional space, so that we can recover the output vectors. Okay? So this is kind of the correspondence between our toy examples and the real shapes in what actually happens. That's actually it for today. The goal of today was to get a sense of how linear algebra, and frankly surprisingly simple math, is what powers these things. And this rotation, stretching, projecting up, projecting down, these are just simple operations that you can understand in 2 and 3-dimensional spaces, and it's quite easy to then get an intuitive sense of what is happening in the actual LLM itself. So yeah, I think I'll stop here. This has been a quick linear algebra interlude before we get stuck into the actual transformer and start looking at cool stuff. Starting with attention, which we'll do in the next episode. See you guys then.